Gay-Lussac's law. Gay-Lussac's law shows the relationship between pressure and temperature. It states that P equals KT, or P1 divided by T1 equals P2 divided by T2. In the equation P equals KT, P stands for pressure, K stands for a constant, and T stands for a temperature in kelvins. Pressure and temperature are directly related according to this law, so as one increases or decreases, the other also increases or decreases. If they're not inversely related, in which if one goes up, the other goes down. They're directly related and rise and fall with each other. Imagine the following scenario. Sulfur dioxide at 4 atmosphere and 21 degrees Celsius, or 294 kelvins. We have two parts to the question. If the temperature raises to 30 degrees Celsius, what is the pressure? And if the pressure is lower to 1 atmosphere, what is the temperature? Answers need to be rounded to 3 significant figures. Before we can do anything, we need to solve for K. So we set up our equation, and we can do it both ways. So 4 is our pressure, and 294 is our temperature. In order to isolate K, we need to divide both sides by 294, and our K in both ways of writing the equation is 4 over 294. All right, now that we have K, we can solve for the pressure of sulfur dioxide at 30 degrees Celsius. So we plug in our constant and our temperature into our P equals KT equation. And if we multiply 303, which is equal to 30 degrees Celsius, or 303 kelvins, which is the same as 30 degrees Celsius, by 4, and then divide the whole thing by 294, we get approximately 4.12 atmospheres. And we have 3 significant figures, and that seems about right, but we need to check it. So 4 divided by 294 equals 4.12 divided by 303, and we get approximately 0.14 equals approximately 0.014 equals 0.014. Our approximations are equivalent. Both sides of the equation are equal in this, and we have done this part of the problem correctly. And in the second part of the question, we had to find the temperature of sulfur dioxide in kelvins at 1 atmosphere. So again, we set up our P equals KT equation. In order to solve for T, we need to isolate it. So we need to multiply both sides by the reciprocal of 4 over 294, which is 294 over 4. 294 divided by 4 times 1 equals itself, and when we divide 294 by 4, we get 73.5 kelvins, which is equal to our temperature. And we have 3 significant figures, and that's good, but we need to make sure the values are equal on both sides of the equation. So on one side, we have the 0.014 from our K, and 1 divided by 73.5 equals approximately 0.014. We've done this problem correctly. So you can see that even as the pressure or temperature may rise and fall, if you know what the initial temperature and pressure are, you can see that no matter what, both sides of the equation are going to be equal if you compute it correctly. So this is how you can prove Gay-Lussac's law, by using any pressure or any temperature variant from your given original problem. My works cited are on this screen, and this concludes my presentation on how to prove Gay-Lussac's law.